So in this video, we will continue our work with properties of negative exponents. We will work on some more examples, and then we will also talk about using negative exponents when the base is a fraction. So those are called quotients of negative exponents. So a little short review of the work we did in the last video. Just a reminder that when we have expressions that look like this, x to the negative n, where your exponent is a negative number, that we can rewrite that expression as the reciprocal of x to the n. So we will take the reciprocal of the expression and change the exponent to a positive exponent. In the second case here in our table, we notice that the denominator has a term or an expression that has a negative exponent, and how we rewrite that is that we move the term up to the numerator. It becomes x to the n, and our exponent, we change the sign on the exponent to a positive. Then this third case here in the table, notice that both the numerator, the term in the numerator has a negative exponent, and the term in the denominator has a negative exponent. And how we handle that is that we will switch places. The term in the denominator moves up to the numerator and its exponent changes sign, and then the term in the numerator goes down to the denominator and its exponent changes sign. Notice the bases stay the same, so the only thing that's being changed when you move these terms is the sign on the exponent. So now let's use these properties to do some more examples. So in this next example here, you notice that we have an expression that involves a fraction, and that some of the factors in the expression, some have positive exponents and some have negative exponents. In the numerator, the x to the negative 2, we're going to have to rewrite that factor because we want our final answer to have positive exponents only. And then in the denominator, we're going to have to take care of the y to the negative 9. The other factors in both the numerator and the denominator, notice they already have positive exponents, so they're going to stay where they're at. So that means that in the numerator, y to the 5th and z, they're okay. But that x to the negative 2, we're going to move it down to the denominator and change the sign on the exponent. And that's because, again, remember we saw that in the table that x to the negative 2 can be written as 1 over x squared. That's the same answer we get if we move the x squared down to the denominator of the fraction. In our original denominator, the x to the 4th had a positive exponent, so we're going to keep it in the denominator, but the y to the negative 9 is going to need to move up to the numerator, and when it does that, it changes its exponent sign to a positive 9. And then the z to the 7th, it stays in the original spot in the denominator. So that took care of the negative exponents so far, didn't it? But now we're going to combine the terms that have the same basis, and for that we're going to use product rule. So product rule, remember, that tells us that we combine powers of the same base by keeping the base and adding the exponents. So that means we're going to use product rule on these two terms and on these two terms that have the same base, and we're multiplying powers of those same bases. So the y's, we end up with y to the 14th, and then here's our z over, and then with the x's we get x to the 6th, and then here's our z to the 7th staying where it's at. Okay, that's taking care of the x's and the y's. But now we've got these z's, and these z's, we have a z in the numerator and a z in the denominator, so that's a quotient, isn't it? That's a division problem. So now we're going to use quotient rule. For the z's, we use the quotient rule. And what that tells us is that when we divide powers of the same base, we keep the base and subtract their exponents. I'm going to give you a tip. Notice that in this fraction, our bigger exponent is in the denominator, isn't it? So instead of bringing this z to the 7th up to subtract from the z to the 1, the exponents 1 minus 7, instead of doing that, I'm going to actually bring the z to the 1 down and subtract from the 7 z's that I have, those 7 factors of z that I have down there, so that I have a positive exponent in my final answer. So here's what's going to happen. You have the y to the 14th is still there. The x to the 6 is still here, but now here you're going to go z to the 7 minus 1 and subtract those exponents with the quotient rule. And so you're going to end up with y to the 14th over x to the 6, z to the 6. In case that seems a little strange, let me show you what we just did. Remember that the original problem here, that we can think of that as, and I'm just going to look at these z's here, having one z in the numerator and having 7 z's in the denominator like that, right? And basically what we've done is that we have reduced one of the z's from each of those, and that leaves me with 6 z's in the denominator, which is exactly what we arrived at, the same answer when we just subtracted that 1 exponent from the 7 exponent that was in the denominator, where we had the bigger exponent for z. Hope that makes sense to you, and we're going to keep practicing that. So we're actually going to practice it in number 11 here. So take a look here, and this number 11 has just z, so only one base, so that's cool. And we are going to use our order of operations first, and we definitely have to take care of this denominator first. And if you recognize that as power rule, you're absolutely right. We're going to have to multiply those exponents and we get 12. So z to the 12. Now when we apply the power rule, and now look at how we have a quotient rule problem here. Just like the last example where we had more z factors in the denominator than we have z factors in the numerator, and we can see that because we have the bigger exponent in the denominator, then we're going to go ahead and subtract those exponents in the denominator, but then that's going to leave our numerator without a factor, and you know what that means really. What's left behind is a 1. So we are going to put 1 over z, and then you subtract the 12 minus 2 with the quotient rule. You subtract those exponents. So you get 1 over z to the 10th. And again, just like in the last problem, remember that z squared means that you have 2 z's, z times z, and z to the 12 means that you have 12 z's, right? 12 of those, and you are reducing 2 of the z's and ending up with 10 z's here and a 1 there. Do you see? If you can visualize that, then these rules kind of make sense, don't they? So 1 over z to the 10th. The rule allows us to not have to do all this expanding here with all these z's. We can shortcut that. Number 12 here, we once again have a parenthesis in the numerator that has, with our order of operations, we're going to have to take care of that first, aren't we? That's a power rule. So let me rewrite this here, and then I'm going to use the power rule here. So we're going to use the power rule. Now, one thing I want to remind you is that this exponent, we're going to multiply exponents with the 8 in the x to the 8th, but then please don't forget the 5 has a little invisible 1 exponent, and it needs to be squared as well. So we're going to square 5, so that's 5 squared, and then here, x to the 8th squared, you know that's x to the 16th, where we multiply exponents and keep the base, and that comes from the power rule. And then we still have this x to the minus 5 from the original problem below. But we have to take care of that x to the minus 5 because it has a negative exponent, and we know that means that we can bring it up and rewrite it with a positive exponent if we move it to the numerator, because that's its reciprocal. So we're going to have 5 squared x to the 16th, and this x to the minus 5 that's in the denominator, it's coming up to the numerator, becoming x to the 5. And there's only a 1 left in the denominator, so I'm not even going to write it. Now, with these two x's, you know that that is a product rule. We're multiplying powers of the same base, so we're going to keep that x base and we're going to add those exponents. So we have 5 squared, which is 25, x to the 21st as our answer, as our final answer. How are you doing with that? Now we're going to introduce you to problems where the base is a fraction and we have a negative exponent. So let's take a look at some of those. So take a look at this box here. Notice it's called quotient to a negative exponent. That means that the base is a fraction, a quotient. So look at this first example. The base is x divided by y, and it's being raised to a negative exponent. And notice what they did. They took the reciprocal of the base. They took the reciprocal of the base. They flipped the base exactly, and they changed the sign on the exponent to a positive exponent. So they took the reciprocal of the base and changed the sign on the exponent. Nothing else changed. And from there, we'll simplify. So you're going to see some examples. Quotient to a negative exponent, take the reciprocal of the base and change the sign on the exponent. So look at number 1. We've got a 3/5 as a base, and we're going to raise it to the negative second power, so we have a negative exponent. And so we just learned about this. Reciprocal of the base, change the sign on the exponent. So the base reciprocal will be 5/3, and the -2 becomes a +2. So reciprocal of the base, change the sign. Okay, now though, we can use our power rule so that we can simplify further, and we're going to square the 5 and we're going to square the 3. Don't forget the 3. Sometimes my students, they'll remember to square the numerator of the fraction, they forget the denominator, so be careful there. And then this gives us 25/9 as our answer. In number 2, same idea, we have a fraction as a base raised to a negative exponent. So we're once again going to take the reciprocal of this base, the reciprocal, and we're going to change the sign on the exponent. So reciprocal of the base, change the sign on the exponent. That means we're going to take 2 over x to the 4th. And notice when I took the reciprocal of the base, I did not change any signs on exponents that were inside the parentheses. Just take the reciprocal just the way it is. You rewrite, you switch the places of the numerator and the denominator only, and then you also change the sign on the outer exponent only. So now we're going to use our power rule for our next step. We're going to cube the 2, and we're going to cube x to the 4th, and you know that that means we have to multiply exponents to x to the 12. And then 2 cubed is 8. So notice how I did not write 6. I did not multiply 2 times 3 here in the power rule. I cubed the base of 2. Just a reminder, we've talked about this before. So that's my final answer. In number 3, same idea. Do you see it's getting very repetitive here, isn't it? So we're going to take the reciprocal of this base, and we're also going to change the sign on the outer exponent. Change the sign. Okay, so the reciprocal of the base will be put the m to the 5th in the numerator, the k to the 8th in the denominator, and then change the sign on the exponent makes a +4. And now we're going to use power rule, this expression. We're going to multiply exponents to get m to the 20th, and then multiply exponents here as well to get k to the 32nd. So same idea, just different numbers, right? Now in number 4, our base is getting a little bit more complicated, and I'm going to invoke the order of operations, and I'm going to remind you that if the base is more complicated, in other words, what's inside the parentheses is more complicated, like as it is here, that you want to try to simplify first if you can before you take care of the outer exponent. And so, do you see that we have 2 y terms there? 2 y factors. So we can use quotient rule first. So I'm going to take care of this inside parentheses first before I do any reciprocals. So I'm going to use quotient rule, and I've got more y factors in the numerator, so my exponent is bigger in the numerator, so I'm going to subtract exponents in the numerator. The 5 stays there, and now I have y squared over a to the 5th. See what we did there? 5 minus 3 in the exponent with the y's. And that's still being raised to the -1. So we've just simplified the base. And now we have a fraction raised to a negative exponent. So we're ready now to do reciprocal and to change the sign on that exponent. So I'm going to flip this base. Notice I'm not changing any signs. I'm just rewriting them in different order. And this outer exponent changes sign to a +1. And boy, we know what that is. If the exponent is 1, then our base just stays unchanged. So here is our final answer for number 4. Okay, with this last problem, number 5, we're once again going to use order of operations. So we're once again going to do some simplifying, and we have 2 things we can simplify. We can simplify the 4 and the 16, the 2 coefficients, and we can simplify the z's, can't we? Okay, so we're going to do that first. Now, careful with this 4 and 16. Those are coefficients. They're not exponents. Do not be doing any subtraction of those 2. You want to just divide. So 16 divided by 4 is a 4. 4 over 1, or 4. I have more factors of z in the numerator, don't I? I have 7 z's in the numerator and only 4 in the denominator. So we will use our quotient rule and subtract the 4 from the 7 in the exponents. And so we will get z cubed, and that is being raised to the negative 4 power. So I'm only dealing with the base. I've reduced it to simplest terms. I haven't dealt with the outer exponent yet, but I'm about to. So I need the reciprocal, and I need to change signs. Now the reciprocal of the base this time is 1 over 4z cubed. And then changing the sign makes it a positive 4. And now we're going to use our power rule, and everything gets raised to the 4th power. Everything. I'm gonna write 1 to the 4th, just even though I don't need to. I could do that in my head, but I just want you to see that I raised everything to the 4th power, not just the z. Okay? And then 1 to the 4th is just 1. Any power of 1 is 1. And then 4 to the 4th is 256. And then we have our z12. And that is our final answer. So I hope you're feeling better about these negative exponents. Go to the next video where we're going to show you what to do if the exponents are fractions. Yes, fractions.